welcome Emeka, which will tell you stuff about this.
Hello. Yes.
Maybe need to maximize it.
Oh, yeah. Sorry, very interesting desktop there. That's a good start. But yes, I'm Emeka, and from Nigeria, and I'm here to tell a story about a problem we faced back home and how we try to solve this with existing applications. And then hence my title, Building Resilient Python Apps for Unreliable Networks. So this is going to be a technical discussion of sorts. I'm going to try and balance not having too much technical things to bore you to death, but also tell the story so you can understand the problems we're trying to solve and how we're trying to solve it. And then we're going to talk about the opportunities. In this presentation, we're going to talk about the opportunity we faced, the solution we proposed, the background information, a case study of how we solve this problem, and then other applications I see of this in the future, because I believe there are other ways we can build on this in the future. And then hopefully we have time for questions. So some months ago, a friend met me and told me, oh, Emeka, so I have this opportunity to build an application for the government, right? And now the government wants to be able to digitize collecting revenue. Now, when you're thinking about collecting revenue, in this side of the world, it's different from back home in Nigeria. In this side of the world, we have, more refined processes where, for example, from the safety of your bedroom, you can, go to your phone and then apply for your taxes or collect revenue. And then, it's very, very seamless, right? But you have to understand that most of the population in Africa and Nigeria come from places where there's still some introduction to these technologies. And there has to be a conscious effort to be able to adapt all these requirements, right? Now, it's also good to understand that when you're taxing in the government, we have the formal and the informal sector. So we have the informal sector, which does not necessarily have a computer and which does not necessarily want to have a computer, but you still want to collect payments from them. And then because of the distribution of these people, so not everybody is in urbanized places. They are in places that have good internet supply or bad internet supply. The office is where they go to, collect these remissions. So when we are building this, we didn't want to just build something that would build for just building sake. We wanted to build something that actually fit our use case. And then obviously there are constraints, right? It's not purely academic, right? The state had 20 plus local governments. So different places that didn't have the same amount of urbanization. Now, they also had 50 plus agents. So these agents here mean, for example, someone in the government office that had a computer, that had access to extremely good internet. Obviously, they have varying levels of connectivity to internet. Not everybody has the best amount of internet or the best connection to internet. But they did have internet. That's one thing. They are not totally offline, right? They did have some form of internet. Then 100 plus users. Remember, any technology you introduce must, for example, cater to the fact that these 100 plus users don't have all day to spend with you. They have other things they're trying to get to do. So anything you're integrating must be seamless. It must not waste their time. It must have the least restriction as possible. And then we also have to do something that was efficient because you're doing a large volume of transactions. So this a large amount of transactions, even though they are microtransactions, you have to make sure that it's still efficient to be able to take care of all these transactions as they pour in. And that's how we came up with this solution, right? So this solution we came up with, I'll get to the name later on, was a web application, right? And then we tried to look at all the different constraints I just explained in the previous slide. So like I said, the first thing it had to be least disruption. In the previous, I just talked about least disruption for the people that come to pay tax. We also have to make sure there has to be least disruption for the agents that are collecting the tax as well. Then there has to be independence. So the different agents that collect this tax should have the least dependence between themselves. And then finally, we should have to work with minimal connectivity. So issues with synchronization and reconciliation have to be at the forefront. And then I put a cute quote I like, that we talked about when we are building this, that even though the advance of technology is based on making it fit so that you don't have to really notice it, so it's part of everyday life, it has to be seamless. And then we came across these very, very nice data types called the CRDTs, the conflict-free replicated data types. Now, this is an abstract data structure. And the good thing about it is that it can be replicated across multiple computers in a network. So remember, these computers are different sections. They're not all together, but there are multiple computers in the network. And these computers are replicas, right? It's the same system that we're deploying in all these different networks. Now, even though they are replicas, the good thing about CRDTs is that CRDTs allowed replicas to be updated independently and in parallel. So, for example, one agent that is updating their task does not have to wait for another agent to be done. These are very independent agents in this particular system, and it can happen in parallel. Everybody should let business go on as usual. Let person A not slow down person B. People should be able to conduct their business. And then without a need for coordination between the replicas. So, for example, if an agent A wants to do a transaction B or transaction 1, you don't have to wait for example, coordination between another replica before he does this transaction. Everything should go in parallel. And then they guarantee that no conflicts will occur. Very, very important, because this is very important data. You don't want conflicts that will arise that will cause issues. And this is, I love this definition of the CRDTs, and this is where I got this definition from. But then to further talk about working in offline first environments, or working in environments where we are trying to make sure that the application actually works, convergence is very important. Even though everybody's working in parallel, we need to make sure that in the end, all our data points converge, and then we can have a central data point. And for convergence to occur, two things must happen. Two things are necessary. The first one is something we call safety. So here, safety means that if the two replicas have the same set of operations, that their states are identical. So the good thing about this is that, for example, what I stated in the future is just a replica, right? We have the two agents A and agent B are replicas themselves, and they perform the same operations. And then the good thing about them being the same and then performing the same operations is that we can reap the advantages of deterministic state computation, because it's the same thing across board. So we can be sure that nothing is going to change from it. If we put the same input in A, we're going to get the same results. If we do the same thing in B, nothing is changing per se in the operations. And then it also means that another condition for convergence is also liveness as well. So every operation that is seen by a replica has to be seen by other replicas. So in the end, they have to even though they are working in parallel, in the end, all these different operations have to find a way of coming together to sync, so that each other can see the other's operation, and then they can do some form of conflict resolution. So given the fact that these two conditions occur in any system, there is a high likely chance that convergence is going to occur. Now, apart from convergence, it's good to talk about concurrence semantics. You have different operations that are happening across different replicas. You have different operations that are not necessarily doing the same thing and can counter each other. How do you make sure that things can work concurrently? And then we have these two semantics. There's the happened before, and then there's the last writer wins. So for the happened before, you can consider the replica A and the replica B. So you can see, for example, for the replica A removes a data A, and then replica A also adds a data A, right? And then we can see in replica B, the replica B removes the data A. But then when the sync occurs, because we know that the removal of A happened before adding A, we are sure that A should remain in the state. This is very important for us to understand, because, for example, if we don't have this kind of law set in place, this means that if there's no kind of sync that happens, this means that, for example, the replica B will remove A in its state. But because we have semantics like the happened before, it helps us replicate this or have this some form of synchrony. And then also we have the last writer wins. So the last writer wins is very, very time-based. These different agents, we try to have different timestamps for these different agents. And then when we have different timestamps, it helps us achieve some form of order. And then based on this form of order, we can then say, okay, this happened before. Oh, maybe that's not the right word to use though, but so it doesn't clash with the other one, right? But basically, we can establish some form of order, right? And then when the synchronization happens, we can say, okay, the last operation must be the latest operation, must be the most correct operation. And then CRDTs, how do we implement, CRDTs? CRDTs can be implemented in different ways. I rank them here in according to their level of complexity. So we can use counters, right? Simple increments and decrements. Obviously, the rule of thumb is that the number of increments should exceed the number of decrements. That's for simple counters. You are trying to do a simple counter operation. Then we have registers where we use the time. Time is very, very important in registers. Well, for example, an agent A does an operation, and then we log the time with agent A has done the operation, and so on and so forth. And then from there, we can create some form of order, and then do some synchronization and have the correct data. And then we have the multi-value register, where, for example, in the multi-value register, we handle even more complex cases. And then in the multi-value register, we have the sets. X, and then the version of the particular data we have at that moment. And then we have sets, and then we have graphs as well. So to talk about a case study, this is a very horrible name though, but the reason for this name is because of our hometown. We just tried to bring up some fancy name based on our hometown engine. So we called it the Independent Networked Yielding Infrastructure. It's a horrible name, I understand. But basically, what we did when we built the system was that, so the user, so this system was built with, we had a couple of, we had endpoints, we had Celery on the system, and then we used Kafka because of the producer and the consumer infrastructure. So the way it works, the process flow was that the user starts an operation, user A or user B, the agent A or the agent B. And then when they started this operation, remember, each user has a laptop and then they have their own local Python server. And then when they perform this operation, we saved this operation to a database. Now, this database is always guaranteed to go through. This is their own local source of truth. Then when we save this operation to their database, we then attempted to try a Kafka sync. Because what we are trying to do for each agent is to be a producer, and then the Python online will be the consumers that works on this data we are pushing. So we try the Kafka sync. So let's say at that particular agent that at that particular time that the agent has tried to connect, that the internet is not available, then we trigger a Celery task that says, okay, we're not able to connect to the internet. You cannot work on this at this particular moment. Let's keep this and try this some other time. But the important thing is that, for example, the agent that is talking to a customer can attend to more customers and the business keeps going. So you don't have to slow down to wait for the internet to do some synchronization. You can keep going. And then the good thing about the Celery tasks is, obviously, we can manage it. You can put retries. We can work with the tasks in the background. And then basically, we keep doing this until we have internet we're sure that the internet is restored. And then when the internet is restored, we sync this to Kafka. We sync this to Kafka, and then we can mark this as synced. Obviously, you have to mark this as synced, so you don't have to keep retrying it. But then when we did this, there are different things we had to note, or what I call do's and don'ts. Obviously, you have to make every operation idempotent. For this to work, every operation has to be idempotent, Then also, as I stated in the previous slide, we have to ensure that every exponential backup, ensure that you implement an exponential backup for retries, right? So you have to make sure that even if it fails at this point in time, you keep retrying it as time goes on. On that reason, why it's important to keep retrying this is because, remember, there's an agent A and there's an agent B, right? Every single state must connect to the network for it to have the full picture. If not, there's no full synchronization there, and then there might be vital information lost. Then the last do was, for example, to show sync status clearly to users. Users must be sure of this operations that have been synced and have not been synced. And then don'ts. Obviously, the mantra is never assume network availability. That's why, for example, we had to make sure that for each local device, we had some form of SQLite database that could store the data. And then we are sure, okay, whether there's internet or there's no internet, we'll store the data. This is always going to pass. And then, to go back to our first point, we make sure that we don't block the UI on sync operations. People have to continue going their business. We don't block the UI. And then to ensure that the system has integrity, we don't delete unsync data. We will keep on retrying as much as possible until it passes, but we'll never ever delete the unsync data. And then we don't ignore conflict resolution. So here, this is a code extract I have from when we are updating the entity state. So as you can see, we are doing an upsert. So we're trying to insert, and then when there's a conflict, to try and resolve the conflict and then update. But obviously, every system has its issues. This system is not devoid of any issues of its own, right? Tombstones do accumulate. You have a lot of systems, a lot of times you keep running this, and then on the local system, you've had a lot of duplicates that have not really synced. They do accumulate. Then there's stability as well. And then finally, long sync times. In a perfect world, you'd hope that the agents remember to turn on their internet and to sync, but you have to ensure that you have checks and balances to make sure that this sync occurs. Because if this sync does not occur, you don't have the perfect picture and the system does not actually work. But since those few months, we've had other friends come and meet me to say, oh, let's try and build this out and let's try and build this out. And then maybe it's because I've seen CRDTs, I've used this on other projects as well. So the first project is an archiving project. So basically, a civil war happened a couple of years ago. And now I have a friend that is trying to gather data about this civil war that happened a couple of years ago. And then this means that if you always get the accurate data, you have to go into rural places for the main people that actually saw this civil war happen, and then get their data. Obviously, in this particular use case, we don't use, for example, in the other use case I gave, where we had to have a Python server for each computer. On this particular use case, the mobile devices have to store this locally, then sync with the Python backend. And then someone else met me, oh, we're trying to build a smart grid. Obviously, with smart grid, you're working with IoT here. And then with IoT here, you're trying to make sure that every single device in every user's home is always synchronizing with the network. So we apply that there as well. And then finally, this is some curiosity I have for the system we built some months ago, is that if we could use multi-agent systems to simulate the kind of environments we had then and even get better results. And then this research work dwells heavily on 2 research papers by the same people, give or take the same people, very, very, very good research papers. I'd recommend that you read it if you have some time. If you want to contact me, obviously this is a system in progress. I'm not saying this is the top of the line system, but this is the system that solve the problems we have, and I believe that we can apply to other things. So if you want to contact me, feel free to write me, and we can have a conversation. Thank you very much.
All right, we have quite some time for questions. So are there questions in the audience? There is one in the middle. Can you keep your hand raised so that can find you? Perfect.
Thank you. My question is, can you please give us a bit more context on the type of conflicts that happened? I'm struggling to imagine for taxation what kind of conflicts, because people usually live in a specific location, and how do conflicts actually occur in your system?
Exactly. So even though people live in the same location, you have to also understand that, for example, for agent A and agent B, for example, let's say I come to pay revenue or something. I might have met agent A today, then tomorrow I'll come and meet agent B. So you see, if these systems are not synced, you see the conflicts already arising, because this might give us conflicting data on what have you done today, what have you not done today. So that's a sign of conflicts that can happen as well. Yeah.
All right. Are there other questions? Back there, yeah. Wait for the microphone, please.
For users who have not yet been fully introduced to have access to the technology, how much of what you do is aiming to be supporting mobile instead of relying on laptop? And is Python usable in mobile settings and deployments?
That's a very, very good question. Very, very good question. I would say so I don't advocate for using Python just for the sake of using Python. So in mobile instances, we just had to use the local storage on the devices. That was the most practical thing to do in that scenario. So yes, I'll say for mobile devices, it made sense to use local storage and then, sync with Python. The only good thing about Python here in this particular infrastructure is that, remember, Python has to do the reconciliation up there to say, okay, this particular query is coming from mobile phones. What are these queries? Because these are different agents. How can we reconcile? Oh, this is what's happening here against what is happening here. But for phones, I don't advocate using Python for using Python's sake. Local storage makes sense. You use it there and then sync it. Obviously, syncing must happen eventually for this to work. So, yeah.
All right, there's a question over there.
For the long walk. I wanted to ask, you said one of the things happened before. So if they are not in sync, how do you know which one happened before? Because you cannot trust the time on the machine. The clocks may be out of sync, I would say. So how do you really know which one happened before? Is it, you said, I think, that the one which stored in the database, the central database, that one is the first. But if they are out of connection, what happens then?
Yeah, that's a very, very good question as well. So something I forgot to mention is that last writer wins. The assumption there is that every single agent has the same time. So that's the way of ruling out, for example, clock being out of sync. But if your clock of a device is out of sync, for example, with the other devices there are other ways of knowing as well. So, for example, there are some heuristics in CRDC that say prioritize the adds only before you do the deletion. And there are some that say prioritize the deletion before doing the additions as well. So there are other heuristics that help us, for example, do the conflict resolution and then not necessarily depend on time. Because time can also, like you said, can be a very shaky, thing to use in some situations. So sometimes you can prioritize on the operations that add to the database, and then later we'll do the removal. Or sometimes you can do the removals and then do the additions, and then we'll balance it up. I don't know if that answers your question. Oh, okay. Hopefully, we can talk later about it then, yeah.
All right, are there more questions? Otherwise, I would have a question. So is it, if you have a conflict that's not resolvable, or can this happen, that kind of still is in an error state where it can't continue to work, or is it, you try as hard as possible to avoid that it's in a non-working state, but does it still happen in practice, and what's to do then?
In practice, I always go for keep as much data as possible, right? Because I believe that data that is deleted is gone forever. So the good thing about CRDTs in theory is that conflicts should be resolved at the end of each sync cycle. But then in practice, I tend towards keeping the data and then trying to maybe reach out to the customer that has come to keep this data than deleting the data, because that can have very, very adverse side effects. So yeah.
All right. So you kind of manually resolve it then, or with some engineer.
Exactly, yeah. Also, it's also good to understand that when we build applications, we don't just build it for ourselves, right? So when we have situations like this that require some kind of resolution, we have to reach out to the customer to say, okay, this particular data, and then we'll see ways of trying to walk back. But to be fair, those kind of things don't really occur that much, where you cannot, for example, say, this is very, very, very complicated. So, yeah.
Okay. We have still time for questions, so over there. Nice how you just choose to do it on the opposite side of the room to keep him fit.
Yeah, thanks very much for the talk. Very interesting. I wanted to ask, given that the agent don't always have the opportunity to sync, do you have any contingencies against hardware failures to not lose data on the edges?
So remember, the system is not built on absence of internet connection. It's built on some form of internet. You have to have internet connection, right? So that's the assumption we always have, right? So for some other projects we've done in the past, what we've had to do when we've had instances where we've not seen a lot of long sync is, for example, you literally have to go to the site and, for example, make sure you have internet connection. In the end, you cannot innovate past some certain infrastructural problems. You have to find a way of making sure that the person syncs there, right? Then in some other situations as well, since, for example, we have a SQLite database, you can, for example, manually export this data and then go somewhere that has better internet connection and then be able to run this sync as well. But like those are very, very, very extreme circumstances, and obviously it's not very scalable if you're trying to do multiple locations at once. But sometimes you have to do what you have to do to make sure that things work, right? So, yeah.
All right. Are there more questions?